In this lesson, we're going to go over the arc length of curves. Now, from Calculus 1, we know that this quantity, the definite integral of a function from a to b, measures the area between the graph of f of x and the x-axis for x between a and b. So this gives us an area. However, many times, as we'll see in applications, we would like to know the actual arc length of a curve. So if we have a graph of a function down here, and say this is the point a, f of a, and this is the point b, f of b, we would like to know the length of the curve as we move from one point to the other. So think of this as being a string. We would like to know the length of that string. You see, this quantity up here will tell us the area bounded between the graph of the function and the x-axis, but we want to know what the length of this curve is. And as we'll see, there are some good applications related to that. Now, to do this, we'll see that we can actually employ integral calculus. So to start, what we're going to do is we're going to approximate this curve with little line segments. So if we take the interval from a to b, and we'll start by partitioning it into n subintervals. Now in this picture right here, we have it partitioned into 4 subintervals. Now we're going to plot the points, the corresponding points on the graph of the function. And then what we're going to do is connect these dots with straight line segments. Now, we know how to calculate the length of a straight line segment. So if we calculate the length of each of these straight line segments and add them up, that would be a good approximation to the arc length of the curve. So let's determine the length of one of these line segments. Let's just focus on, let's say we'll focus on this line segment right here. So we'll consider this one right here. Now we want to calculate the length of that segment. Well, if we draw a triangle like this, we can employ the Pythagorean theorem to calculate the length of that hypotenuse. Now let's notice that this distance here, that's going to be delta x, where delta x is the length of each subinterval down here. So recall that the delta x is just b minus a over n, where n is the number of subintervals. In this case, the n would be 4. Now the length of this side we'll call your change in y, and we'll denote it with a subscript I. You see, because the delta x, if we use this formula here, the delta x will be the same for each subinterval, but the change in y, well, that'll be different for each one. So if this is the ith subinterval down here, then we'll call it this distance right here your change in y sub I. Now we want to calculate this distance. We'll call that delta s sub I, like that. So by the Pythagorean theorem, we have this result. Right, that just comes from our Pythagorean theorem. You know, a squared plus b squared equals c squared. So the a would be like the delta x, the b would be the delta y sub I, and the c would be our delta s sub I. And then of course you just solve for the c by taking the square root of a squared plus b squared. So this is just a statement of the Pythagorean theorem. Now we're going to manipulate the right-hand side here a little bit. Let's factor out a delta x from this term and this term over here. And what we get is this. Alright, so there we factored out the delta x from this term and this term. Notice if I multiplied the delta x squared back inside here, we would recover this. Delta x squared times 1 would give us this. Delta x squared times this fraction, the delta x squares would cancel and we would recover this back. Now let's move the delta x squared. Let's split this square root apart. Write it as a square root of this term times the square root of this term, and then the square root of delta x squared will just be delta x. So we then get alright, you see what we did is we just took the square root of this term times the square root of what's in the parentheses here, and the square root of delta x squared is just delta x, and we move that to this side. Now let's focus on this term right here. Let's notice that this is actually the slope of our line segment over here, right? You see the slope of that line segment is that quantity, change in y over the change in x. Now by the mean value theorem, recall what the mean value theorem says. It says this. Alright, that's our statement of the mean value theorem. Now what this quantity is it is exactly the slope of your secant line. It's the slope of this line. You see what we have here is the numerator here. This piece right here, that's just your change in f, or your change in y if y is equal to f. And what you have down here, b minus a, that is your change in x. So by the mean value theorem, we know that we can write this quantity here as f prime of xi for some xi in this subinterval down here. So say xi might be like right there. You can also see this result if you look at this graph closely. You see at some location here on the graph there is a point where the tangent line will be parallel to that secant line. And so in other words, the derivative of this function at that point there will be the same as the slope of that secant line, which is change in y sub I over the change in x. So we can replace this quantity right here with this and then rewrite this as follows. Okay, so we've determined that our change in s, that this distance right here is equal to this quantity right here. Now all we have to do is sum all of these up and take the limit as our partitions go to infinity, and we'll get an integral coming out. So now what we can do is write this. So our arc length will equal of all of these terms, sum of all of these terms down here. Now the way I have it written here, this is actually an approximation. However, if we take the limit as n goes to infinity, then you see these little pieces here, these little line segments will hug the curve more and more closely, and we will be getting the exact arc length as we let the number of partitions go to infinity. And of course we recall that this quantity right here in the limit will turn into an integral. We've replaced the x sub I with just an x, and the delta x becomes a dx, and we get our integral formula. And there you go. That is our formula for the arc length. So the arc length of a curve for x going from a to b is the definite integral from a to b of the square root of 1 plus your derivative squared. And now we have this result stated precisely down here, and we'll look at a few examples as well. Now here's a statement of the result we just found. If we're given a smooth function, y equals f of x, on the interval from a to b, now smooth meaning that the derivative must exist for every x in the interval from a to b, then the arc length of your function or curve from a f of a to b f of b is given by this formula right here. The arc length is just the definite integral from a to b, square root 1 plus your derivative squared. So let's take a look at this example. Let's find the arc length of this curve for x between 0 and 4. Now we will need to take the derivative, we see, so let's take the derivative of this function, so y prime. So there's our derivative, of course. And so the arc length of this curve from 0 to 4 is given by and there we go. We just have to evaluate this definite integral. Notice 3/2 times the square root of x squared is just 9/4 times x. Now we need to find an antiderivative for this function and then evaluate it from 0 to 4. Now we could do a substitution. We could let u equal 1 plus 9/4 x. What's under the square root? But let's try to do this one in our heads quickly. So we know that the antiderivative is going to be some multiple of this function. Notice that if I were to differentiate this, we would drop the 3/2 down and subtract 1 from the 3/2. That would give us the square root of 1 plus 9/4 x. However, we would have a 3/2 out in front here, and we don't want a 3/2. So we need to multiply this by 2/3. Now if we were to continue differentiating this, we would have to use the chain rule, right? So we drop the 3/2 down, that cancels with the 2/3, and we subtract 1 from the exponent, so that gives us a square root. But then we need to multiply by the derivative of the inside, which is 9/4. We don't want a 9/4 here, so we have to multiply by 4/9. And here is our full antiderivative for the square root of 1 plus 9/4 x. And then we need to evaluate this from 0 to 4. So let's see, this is going to be 8 over 27. Now if I put the 4 in here for x, we get, then we need to put the 0 in here for x. And there we go, we get our answer. So the arc length of this curve for x between 0 and 4 is 8 over 27 times 10 to the 3/2 power minus 1. Note 1 to the 3/2 is just 1. and you could evaluate this on your calculator, of course. It comes out to be approximately 9.0734. And so that is the arc length of this curve as x varies from 0 to 4. Now, if you did prefer to use substitution to do this problem, you would let u equal 1 plus 9/4 x, in which case du is 9/4 dx, and then this integral would become, now if we put 0 in for x here, the u becomes 1. If we put 4 in for x, the u becomes 10. dx will equal 4/9 du, taking the 9/4 over. This becomes the square root of u, like that. And then this equals, now the antiderivative of this of u to the 1/2 is 2/3 u to the 3/2. And you see we're still getting that 8/27 out in front here being multiplied as a constant. And then we evaluate this from 1 to 10, and you see we get the exact same answer. Which is the exact same answer we had before by using that shortcut method for finding the antiderivative of the square root of 1 plus 9/4 x. Now let's take a look at this example. So we want to find the arc length of this function for x between 1 and 2. Now this might seem like a strange function to find the arc length of, but you'll see that a lot of these problems, the functions are a little strange looking, because in order to be able to find an antiderivative of a function like this, we need what's underneath the square root to be a perfect square. And so the functions that will do that for us are sometimes a little bit contrived looking. So let's try this problem here. So we just have to use this formula up here. So we need to know what the derivative of this is. Well, y prime, of course, is going to be so there's the derivative. Note that, of course, that the derivative of 1 over 2x, that's 1/2 x to the negative 1. When you differentiate this, you drop the negative down, so that's where that negative comes from, and you subtract 1, so you get x to the negative 2, so 1 over x squared. So that's where that piece of the derivative came from. So now the arc length So here's our arc length. Now let's FOIL this out, and we'll see that what's underneath the square root will become a perfect square with a little bit of algebra. Now notice if I take this term times this term, the x squares cancel out and I get negative 1/4. And then when I go this term times that term, foiling it out, I'm going to get another negative 1/4. So that's where that negative 1/2 comes from. And then this term times itself is going to be now 1 minus 1/2 is going to be positive 1/2. Now let's factor out of away from each of these terms a 1/4, in which case we're going to get this. So just notice when we pull a 1/4 away from each term, we're left with next to the fourth here. Pull a 1/4 away from here, we're left with 2, because notice if I multiply 2 by 1/4, that gives me back the 1/2. And if we pull a 1/4 away from this term, we get 1 over x to the fourth left over. And then moving the 1/4 outside of the square root, it will become 1/2. Notice if we move this 1/2 back inside the square root, it will become the 1/4 again. Now this term right here is a perfect square. Notice that this is equal to this squared, right? Because notice if I go x squared times x squared, it gives us this. X squared times this term will give me 1. This term times x squared will give us another 1, so that's recovering the 2. And then this term times itself gives us the 1 over x to the fourth back. So now this integral then becomes and there we go. Now we just have to find the antiderivative of each of these terms, which isn't too bad. And antiderivative of x squared is x cubed over 3, of course. Antiderivative of x to the negative 2, we have to recall that you just have to add 1 to the exponent here. So that gives us x to the negative 1. And divide by negative 1, which is equivalent to just multiplying this by a negative. Notice if we differentiate this, drop the negative 1 down, we get a positive, and then subtract 1, we get negative 2 back. And now we just have to evaluate this at 2 and 1 and subtract, and we get our answer. And there we go. Notice if we put the 2 in here, we get 8/3 minus 1/2, putting the 2 in for the x. And if we put 1 in for the x, we get 1/3 minus 1, 1 over 1. And there you go. That is the arc length of this curve as x varies from 1 to 2. So just notice what we had to do here. We just had to FOIL this out after we took the derivative. And then we just had to do some algebraic manipulation to see that what's underneath the square root is actually a perfect square. And then the problem was easy from there. Now that won't work all the time, of course. In fact, normally that doesn't work out. It only works out for rather special functions. So oftentimes we're left with evaluating something like this numerically, either using a trapezoidal or Simpson's rule. And finally, let's take a look at this example. So we have a cable that is strung between two towers that are 200 feet apart, and we're given that the cable hangs in the shape of a hyperbolic cosine function given by this equation. We want to find the length of the hanging cable. Now, it might seem strange, why do we use the hyperbolic cosine or cosh function? Well, that is actually the shape that cables hang in. And we'll prove that in another video. So this actually is a fact. For example, telephone wires hang in the shape of a hyperbolic cosine function. So anytime you're driving down the road and you see a telephone wire, you can be reminded of your calculus class. Isn't that nice? So for this example, we have two towers here that are 200 feet apart. And then we have a cable that hangs in between them in the shape of a hyperbolic cosine like that. And we want to find the length of this cable. So all we have to do is apply this formula right here. So we'll need to take the derivative of this function. So taking the derivative here, let's note that y prime. Now remember, derivative of cosh is actually positive sinh, not negative sinh. That's the trigonometric cosine function. Derivative of the trigonometric cosine is negative sine. But for the hyperbolic, it's just positive sinh. And then we have to apply the chain rule here, so now we need to multiply by the derivative of the inside, right? Which is going to be 1 over 150. So that's nice because these 150s cancel, right? We had to apply the chain rule here with the inside being a u. So we differentiated with respect to u first. So that's where this came from, 150 sinh of u times du dx. Now we just need to plug everything in this formula right here. Now we're just going to integrate from 0 to 100. Okay, that's because we're going to set up the x-axis like this. Let's just think of, so we're going to think of that as being the x-axis, and this is x equaling 0, and so this would be x equaling 100 here. Negative 100 would be over here. And so we're just going to find the length of this portion of the cable and then multiply our answer by 2. So the length is going to be 2 times the integral from 0 to 100 of this up here. So now we have to calculate this quantity. Here's our derivative down here, so it's going to be the sinh squared. There we go. Now if you think back, we have to try to solve this here somehow, figure out how this is a perfect square in here. Well, remember there is a hyperbolic identity that we can use, and it states that so look back through your list of hyperbolic identities and you'll see this one listed. So if we take the sinh over to the other side, we see that 1 plus sinh squared equals cosh squared. So we can replace everything in here with a cosh squared of x over 150. And so then this integral just becomes So now we need to find an antiderivative for the cosh of x over 150. Well, that's a pretty easy substitution. You could, at this point say let u equal x over 150. But we can figure this out in our heads if we think about what the antiderivative of cosh is. So this is going to be twice the sinh. Now it's going to be the sinh of x over 150 times some constant. So let's think about this. If we differentiate the sinh of x over 150, we'll get the cosh of x over 150, but then we need to multiply by the derivative of the inside, the u term here, which is going to give us 1 over 150. Right? That's what we would get if we differentiate. Right? This would become a cosh, x over 150 times 1 over 150. This being the derivative of the inside. Now we don't want a 1 over 150 here, so what do we have to do? Well, we need to multiply this by 150 then. So our antiderivative here would then be 2 times 150, or 300, times the sinh of x over 150. Just check it out. Once again, if you differentiate this, you see you get 300 times the cosh of x over 150 times the derivative of the inside, which is 1 over 150, and well, the 300 would be out here, and then you get 300 over 150 gives you your 2 back. All right. Then we need to evaluate this from 0 to 100. And so what we get then is 300 I'll just move the 300 away from the evaluation of this portion. So we get 300 times the sinh of 100 over 150 minus the sinh of 0. Now remember the sinh of 0, that is 0 if you think back to how the sinh is defined. This is 0. And we end up with our answer, which I will put over here. And there's our answer. 300 times the sinh of 2/3. 2/3, of course, coming from 100 over 150. And if you want to evaluate this and your calculator doesn't have a sinh function on it, you can just go back to the base definition for what the sinh is. So this would be So remember, sinh is e to the x minus e to the negative x over 2. So in this case, x is 2/3. So e to the 2/3 minus e to the negative 2/3 over 2. And then that is approximately 215.148 feet. And so that's how long this cable would be. And that concludes our lesson about arc length.